I really want to repeat all that. Okay, so in calculus, guys, in calculus, we are going to be, especially in BC calculus, we're going to be calculating what we call an integral. Can you all see that in the back? Trying to figure out how big I need to write. Okay, we're going to be calculating an integral. And another name for an integral is an antiderivative. And an antiderivative is kind of going backwards from a derivative. And like I mentioned a second ago, a derivative is going to calculate a slope or a rate of change. A velocity is an example of a rate of change or speed. Acceleration is an example of a rate of change. Any kind of growth, whether it's a growth of an industry, all that can be measured by rates of change. And people use derivatives, whether it's physics or economics, all kinds of different applications. And that's what calculus is all about. It's about studying rates at which things change. And sometimes calculus feels a lot like just math, like you're crunching these numbers and you really don't know what you're doing with them. But a lot of times you're doing applications of those derivatives. And it really actually is, to me, one of the cooler subjects that's out there. Calculus, really, it's very simple in its construction, but its application is very diverse. And I know I sound maybe a little mathy like that, but I really do think for all the stuff that you learn and you're like, when am I going to use this junk? So much of that becomes realized when you start getting into calculus. It really is a cool application of math and not just like memorization, like conic sections or whatever. So an antiderivative is what an integral is. Well, an integral has this funny sign. It kind of looks like a little S, but it's kind of, some of them in your book, it might be slanted a little bit. It's got a little hook on each end, but it's an integral. And when I integrate a function, let's just say I was integrating some function like 2x cubed minus 5x. And you can ignore what the dx means, don't worry about that. But when I integrate this, I go from a rate of change equation back to an original equation, okay? And that new function I get, and again, you don't have to worry about all the plus c and the dx, don't worry about it, that's calculus, we'll get to that next year. But that new function I get is the antiderivative. Well, sometimes when it comes to integration, the rules that we have won't work for us. So what happens when I get this function, and it usually is some kind of a fraction, like a function over a function. What happens when I get stuck and all of my rules don't work? Well, this process I'm going to show you today, called partial fraction decomposition, allows me to take this function and write it in a much more simple form. And that's the idea of what we're doing. Now, we're not going to do any of the calculus today. What we're going to do is the algebra. I'm going to show you how to take fractions that are very complex, that I don't know the rules of how to integrate them, and I'm going to break them up into smaller fractions that are equal to that original fraction. It'd be like me taking a whole number like 5 and breaking it up into a bunch of parts, you know, like 2/3 and 1/3 and 5 and 3 and then 1. And all of those things added together will give me that original fraction. So that's what I'm doing with partial fraction decomposition, okay? So I just wanted to mention that as to why we're doing this, because you might look at it and go, why am I even doing this in the first place? That's the reason. So that when you get to BC Cal, or if you take AB Cal next year, and then you go off to college and you take Cal 2, you'll have an idea of this. It won't be something new to you. And you'll go, oh yeah, I remember partial fraction decomposition. That was not so bad. So here is an example of partial fraction decomposition. And I'm going to start you pretty basically with a couple of really simple ones. And you might have even recognized some of these from some of the ciphering that we did last year. You might, but this is where we're going with what we're doing today. So hypothetically, what if I had a fraction like this, and again, what I would really be doing, and you don't have to write this part, I would be integrating this fraction, and the problem is, right now, my strategies for integrating this fraction don't work. I would be stuck. So what I would want to do is rewrite this fraction as you don't have to write this part down, as a sum of two fractions so that I could actually integrate. But what we're going to do right now is forget about all the integral stuff, and we're going to focus on how would I rewrite this into two smaller fractions that I could actually add together and integrate separately with the rules that I know. Okay, so the first thing you're going to want to do is factor that denominator. Okay, so when I factor this denominator, and if it didn't factor, we'll talk about that in a second. We're going to factor that into x, 3 to what, negative positive? And I'm going to take these two terms and I'm going to break them up into two separate fractions, and they are going to represent my denominators. Okay? And I do not know what the numerators are yet. That's what I'm going to be trying to figure out. Okay? So, how do I figure out what the numerators are? And I don't need this right here anymore. I can do this. So, here's what you're going to do to start the process. Here, you're going to look at the bottom, and if you see what we call a linear term, you know linear looks like mx plus b, looks like a line, and those kind of look like lines to me, right? 1x minus 3. If it's linear, right there, then you're going to put a constant on the top. So a constant would, and I'm going to show you enough examples that this is going to make a lot of sense to you. So because these are both linear, and linear is like ax plus b, we're going to put a constant, which basically means we're going to look at that as 1 power less than a linear would be a constant. And since I don't know what these two constants are, I'm going to put a for one and b for the other in the chance that they might be different. Now I'm going to give you a couple what ifs. If the bottom part was not linear, let's just pretend for a second. What if the bottom part ended up being something like this? This is now not linear, this is quadratic. Well, if it's quadratic, what's 1 power lower than a quadratic? Linear? So what we're going to do is put a linear expression. Ax plus b there. But this is linear, so what do you think I'm going to put here? A constant, and since I've already used a and b, we'll use the constant c. This is a pretend. We're just kind of giving you some examples. Now, pretend. What would happen if one of the fractions was cubic? And again, we're assuming that I can't factor it anymore. If I can factor it, I'm going to want to factor it. We talked about that on this original problem. But if I can't factor it, I'm starting to split it up. What if I split it up and got a cubic and a quadratic and a linear? What would I put on the top, do you think, if it's cubic? What's 1 power less than that? Quadratic. So for the top, I'm going to go ax squared plus bx plus c, which is a quadratic expression. And if it's quadratic, what am I going to put on the top? What's 1 power less? Linear. So I've already used ABC. So dx plus e, which would be a linear expression. And this one's linear. What's 1 power less than linear? Constant. Since I've already used all the way through e, I'll use an f. And I'm going to do that all day long based on how I factored this problem. But because this one was two linears, I just wrote the two linear factors there, and I put constant, constant. Y'all seeing that? Okay, there's a couple other things I'm going to have to throw out there, but this is enough for now. So now, what do? Our goal now is to figure out what A and B is. So because we're going to assume that this equation is true, and again, if you didn't hear me, this is called partial fraction decomposition. Because we're decomposing, I guess, this into a bunch of partial fractions of this bigger fraction, or higher ordered fraction. So anybody got an idea how I would solve for A and B? Just a hunch. So anything you especially don't like about this equation? You can really hear him, can't you? He's got one of those TV screen boards that's right mounted on this wall, which makes no sense because every single room it's mounted on the other wall. This one it's mounted on this wall. So anyway, whatever. And Carlson's loud. I think he may be louder than me. I used to be able to hear him when he was in the history pod, when I was in the math pod. If his door was open. Anyway, whatever. So right here, talk to me. What could I do to kind of clean this up? Again, my goal was to try to figure out what A and B is. Anybody got an idea? Might be right. Could be the hero of Monday morning. Okay, and then do what with it? Which the common denominator is that, right? Because that's x minus 3, x plus 2. What can I do with that? Everything by that? So since that's x minus 3, x plus 2, right? I'm going to multiply everything through by x minus 3, x plus 2 and cancel everything and see where I am. So I'm going to multiply this by x minus 3, x plus 2. That's the whole left side. And I'm going to multiply the whole right side by x minus 3, x plus 2. And in doing that, I would distribute it in to both of these. Does that make sense? And when I do that, what happens to the term on the left? So everything cancels, which was my goal. And what happens to this? Only the, what? X minus 3's cancel. Leaves me this. And here only the x plus 2 cancels. And leaves me this. Now, what we're doing here, guys, is we're trying to figure out what A and B makes this true. Now, what that kind of means is it's going to be true for every value of x. For everyone. Well, with the exception of positive 3 and negative 2, which make it undefined. But it's going to be true for every value of x. So I'm working with this, and I'm trying to find the A and the B that would make this equation true. And if it makes this equation true, I'm going to assume it makes the top equation true. And if it does that, I will have found the partial fraction decomposition. Now, if you look in the book does this kind of weirdly. And you might remember this problem from the very first week of Algebra 2. You might not. But in the very first week of Algebra 2, you were given an ugly problem like this. And one of the strategies that the book taught and that I mentioned to you was, well, if this is going to be true for every value of x, for every one, then couldn't you just, and you don't have to write this or you can if you want, if I multiplied it all out, and this has to be true, then don't all the x terms have to be equal to each other? And then don't all the constant terms have to be equal to each other? So what I could do one way, and this is not the easy way, but one strategy is to take all the x's, x, and set it equal to all the other x's, and then take all the constants and set it equal to all the other constants. And again, if this is true, I could divide each of these x's out, and if I divide everything by an x, I get 1 equals a plus b. And what do I have now? I have a system of equations. And sometimes you have no choice but to do it this way. And sometimes you get you get a big system. This only had 2 variables, a and b. But if you think back a couple problems ago, remember the one that had the cubic on the bottom and you have a quadratic? So you had ABC, and then you had a quadratic, so you had a linear, so that gave you DE. Then you had a linear, so you had a constant, that gave you F. Well, that would be a 6-variable system. I don't really want to solve a 6-variable system of equations. It might work out nicely, but it might be horrible. So so this is a strategy. And if I had a 6-variable system, I would probably have a lot of equations here, right? I'd be comparing x cubes to x cubes, x squareds to x squareds, x's to x's, constants to constants, and I would have a whole bunch of these. Well, I want a better way than this. Although this is a strategy that I might have to pull out occasionally. So here's what I'm going to do. I'm going to be creative. Now, I told you a couple seconds ago that on a partial fraction decomposition, this has to be true for every value of x, right? Well, if it's true for every value of x, why don't we just pick a random, cleverly chosen x that would make solving for a and b really easy? Can you think of an x value that if I plug in here will make solving for a and b really, really easy? Anyone? Yep.
-2.
Why -2?
It'll get rid of the a.
Okay. So if I were to plug, I'm going to say let x equal -2. If I plug a -2 in here, and here, it gets rid of one of the a values completely. And I'm getting rid of all the x values because I'm plugging -2 in its place. So if I were to plug a -2 there, I get -2 plus 7 equals a times -2 plus 2 plus b -2 minus 3, and that 0 right there makes all of that go away. And all I have left is 5 equal -5b, and b is -1, and I completely avoided having to solve that system. Now at this point, if I wanted to, I can take that -1 and plug it back in there. And once I plug that -1 back in here, what am I left with here? I'm left with nothing but a and some x's. And then I could really pick any number I wanted to plug in for x, because all I would have left is a. But what I like doing, rather than plug a -1 in there, because there's a chance I might have made a careless error there, I like coming in here and just doing the exact same thing, but this time not with -2, but with +3. So I'm going to come in here now, and I'm going to let x equal +3, and that gives me 3 plus 10 equal a times 3 plus 2 plus b times 3 minus 3. And again, that's a 0, which makes all of that go away. And I get 13, if I did the math right on that, equals 5a. So a is 13/5.
You gotta add yourself, it's 3 plus 7.
3 plus 7.
Oh, 3 plus 7. I was wondering where I got a fraction. I was trying to make it nice. So 10/5 is 2. Thanks. Are y'all with me? So I found A and B. Now what was my goal again from the very beginning? It was to take this and do what? Rewrite it into 2 lesser fractions that I'll be able to integrate once I learn what integration is, right? And I will have done that once I find the A and the B. Well, I did. So the answer to this is not A is this and B is that. The answer to the partial fraction decomposition is 2 over x minus 3 plus -1 over x plus 2. That is the partial fraction decomposition. And you will see next year that this is a really simple problem to integrate. But this I can't integrate at all. I mean, there are times when I have an ugly fraction like that I'm able to integrate through a process called U substitution. But this particular one, for me to be able to do this, I would need a 2x minus 1 on the top, and I don't have it. But now, this is a super easy problem to do with U substitution, when you learn U substitution. Y'all track with me? Okay, now, I'll show you another one. Because these can get a little ugly. And you gotta have a strategy. Okay, what if you had this? Now on this one, it's already factored, isn't it? And when you have it factored, what would you describe that term as? Constant, linear, quadratic, cubic? Now, if they'll multiply it out, it's a cubic, right? Because it'd be x cubed and a bunch of junk. But right now, that is a linear term raised to a power. So if that's a linear term raised to a power, right, and it's already factored, so whenever you have more than one of a kind of term, like in the last problem we did, we had one of one kind and one of another. There were 2 different linears. But if I ever have the same term more than once, then here's what you have to do. It's a little strategy. You have to write that term out once for each power. So you have to write it out once for x plus 1 to the first. You have to write it out once for x plus 1 squared. And you have to write it out once for x plus 1 cubed. And then when you look at them, these are all linear terms. Now the temptation is to go, wait a minute, that's linear, quadratic, cubic. You're right if I multiply it out, but the way it's factored, it's a linear to the first, a linear to the second, and a linear to the third. So because all of these are linear, what do you think I want in the numerators? Constants. So I'm going to put constant, constant, constant. Now let me give you another pretend. What if I had something like this? 2x minus 1 squared, 4x squared minus 5x to the third over 3x plus 5. If I was going to do a partial fraction decomposition on this, what is this right here? This would be a, what? A linear term to a higher power. So for that linear term, I would have to have one fraction representing the linear to the first power, and I would have to have another fraction representing the linear to the second. Does that make sense? Yes, no? And because they're linear, what would go in the numerators? Constants, A and B. Y'all are just super talkative. Okay, now, what do I have here? Quadratics. And if it's a quadratic to a higher power, what do I have to have for each of those quadratics? I'm going to put dot, dot, dot to make sure this fits in the video. But I'm going to have what? A fraction for the quadratic to the first, a fraction for the quadratic squared, and a fraction for the quadratic to the third. Now, they're quadratics. So if it's a quadratic, what am I going to need in the numerator? Linear, linear, linear. Now I've already used A and B. So what's my first linear? Cx plus D, and then Ex plus F, and then Gx plus H. And honestly, I don't care what variables you use. Don't use X, because I already have X in the problem. Now, if you think about it, this would be a nightmare for you, because you're going to have 1, 2, 3, 4, 5, 6, 7, 8 variables you would have to solve for, which would make the math really, really brutal. The system of equations really, really brutal. You're not going to be asked to do that. Okay, you might get up into a 4-variable equation, and usually there's some tricks to really help you get there, and I'll talk about those today. But I might ask you to expand one, like I might say, write out the initial partial fraction decomposition, do not solve for the variables. And you would just write it out on a test and be done, walk away. Now, if I give you something like this, I'm probably going to ask you to go ahead and complete the partial fraction decomposition, or do it completely. So I'm going to go back to this, but are y'all tracking with me here what we do with powers? Okay, all right, so check it out. What do you do? Anybody, first step? What are we going to do? Common denominator is that. So multiply everything through by this. So here we go. I'm going to multiply everything by an x plus 1 cubed on the left, and then everything by an x plus 1 cubed on the right. And in doing that, x plus 1 cubed, x plus 1 cubed, x plus 1 cubed, I would distribute that in. Now what cancels here? Everything. Gone. And I can bring this down. What cancels here? What cancels? One of them. So when I cancel one of them, I have the a and an x plus 1 squared left. What cancels there? Two of them. So I have a b and an x plus 1 left. And what cancels there? All of them. All right. So what would you do? Pick a carefully chosen x value. Now listen, you can pick any x value you want, but what would be a clever x value to pick? -1, because that would eliminate everything there and everything there and allow me to solve for c. So I could say, all right, let x equal -1. So plugging a -1 in there, you can be careful about this. A lot of people end up missing these problems because of algebra. plugging the wrong number in and not knowing what to do with it. If I plug a -1 in there and square it, it's +2. If I plug a -1 in there, it's -7, and then +4. If I plug a -1 in there, all of that goes away. If I plug a -1 in there, all of that goes away, and all I'm left with is C. So you don't have to show me, I mean, I was showing you in the first problem, plugging -1 into everything, but be wise. So right here we get C is -1. Great, I've got my C term. Now what would you do? See, I don't have any more cleverly chosen x's to work with, do I? But it's supposed to work with every x, isn't it? So if I wanted to, I've got this C value. So if I want, I could take that -1 now and go ahead and plug it in there. And now I'm down to just A and B. Does anybody see any other thing you could do right here? Okay, so if I plugged a 0 in, granted, plugging a 0 in is not going to make A and B go together. I mean, make it go away, but it does make it easier to do the math, right? So she's just picking a random x value. Could be anything, but I'm a big fan of 0 because it makes a lot of junk go away, even though it doesn't make A or B go away. So check it out. I could do this. Let x equal 0, which would give me 4 on the left, and it would give me 1 squared times A, and it would give me 1 times B, and then don't forget -1. And that, even though I don't know what A or B is, does give me an equation. And if I only had another equation, I could solve for A and B, couldn't I? But wait, can't I do this again? Again, I can do this all day long. Sometimes there are values of x that make it really great. But sometimes the values of x, they might not make it great, but at least they get me a system. Is there another x that might be easy to plug in? 1? Why not? I mean, you can plug in 7 if you want and make your life miserable, but I'm a big fan of 0s and 1s and -1s. I've already used -1, so I can't use that again. 2. But if you picked +1, and I'm hoping somebody in here is going, wait a minute, isn't there an easier way to do this? And I'm hoping you have it. But if I plug a +1 in there, I get 2 plus 7 is 9 plus 4 is 13. Here I get 1 plus 1 is 2. 2 squared is 4, 4a. And here I get 1 plus 1 is 2, 2b. And right now, can't I just use what I already know? What I've already talked about on last Thursday, systems of equations? Can't I use what I already know to solve for A and B here? Now, I'm not going to do that right now because I'm assuming you know how to do it, but I want to talk about something else you might have been able to do to make your life easy. Does anybody see it? Rather than do this, what did I do in the very first example? Before we showed you this little cleverly chosen thing, what did I do? So I multiplied it all out. Do you remember that? I multiplied everything out on both sides, and I set the x's equal to each other and the constants equal to each other. Okay, well what if, I'm going to leave this here for a second. What if I multiplied this all out and set the x squareds equal to each other? How many x squared terms do you have? Or would you have had? I would have only had 1 here, right? This is not going to give me an x squared term. That's not going to give me an x squared term. Now it's possible that it does. But in this case, you can see that it's not. The only one that's going to give you an x squared term is this, right? So think about it. What if I just said, well, the left side is 2x squared plus blah, 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 blah. The right side, if I were to FOIL this out, I'd get what, x squared plus 2x plus 1? Wouldn't that give me ax squared plus a bunch of other junk? And if my strategy is to compare x squareds with x squareds and x's with x's, can't I tell right now that if all I do is look at the x squared terms, what does a have to be? And now you have your a value. Are y'all seeing that? And if I have my a value, I can plug that back in. Are you with me? And now that I have my a value, I mean, I could go back and do the same thing with the b's. But look, this is gonna have an x term, a single x term with the b. And look, when I multiply this out, this is also gonna have an x term with the b. But in this case, now that I have the a term, I can go back in there and plug a right in here, right? And if I plug a right in there, I can say, all right, since I have a, I know that b must end up being 3. Now, this doesn't always end up being nice and simple, okay? It just doesn't. Sometimes that initial strategy where you just pick all the cleverly chosen x values that you can, and then sometimes it's just pick 2 other ones, get a system of equations, solve that system. But occasionally you can make it easy on yourself by just comparing x squareds. Sometimes you can go in, there's only one x squared term, there may be only one x cubed term, and you can steal one of your variables that way. So now that I've found a, b, c, is my answer the a and the b and the c value? No, the answer is that over x plus 1. So my answer would be 2 over an x plus 1. And then the b value, 3 over an x plus 1 squared. And then the c value, -1 over an x plus 1 cubed. And that would be the partial fraction decomposition. And this would be something I'd have a better chance of integrating. Not better. This is something that I can integrate with AB calculus. But that is not something I can do. In BC Cal, you'll be given problems like this, and you'll have to write the partial fraction decomposition, and then you'll integrate each part. We won't have to do that in AB, because it's like Cal 1, not Cal 2. You tracking with me? Okay, last couple things. What do I have? 12 minutes? Okay. What have you noticed? Look back at the 2 problems I just did, and even the ones that I set up. What did you notice about the powers of the numerator and the denominator in all of them? The bottom's bigger than the top. And when the bottom's bigger than the top, this is what I do. But if the power on the top and the bottom is the same, or if the power is bigger on the top, either one, what you have to do first is make it where the bottom has a bigger power than the top. How can I possibly do that? How do you take a number that has a bigger, think about just a regular fraction. How do you take a number like 17/3 and rewrite it where the fraction has a bigger number on the bottom? The fraction part. Do what? You make it a mixed number, and you do that by dividing. So right here, I would divide 3 into that, and I would get 5 2/3. Right? So in a fraction that's like this, if the top part, you can see right here, this is a cubed x, this is a squared x. Well, I'm ready to go with partial fraction decomposition. But if I ever look up and the powers of the x's are the same or bigger on the top, I'm going to have to divide first. Do you remember long division? Yeah, everybody's favorite. All right, so long division. You got to remember how to do it. The downside of long division is, well, it's long division. The upside is it's not going to be as dirty as the problems we had in Algebra 2. In Algebra 2, I would give you one that would take like 10 steps, for you to do the division. And on all those 10 steps, there's tons of ways to make mistakes. This one, it's usually just 2 or 3 steps, maybe less. But let me give you an example. So right here is one where the numerator has a bigger power than the denominator. And make sure that you're able to see this. So right here, you've got 4x cubed, 9x squared, minus 2x plus 6, and it's divided by x and x plus 2. Now, when you look at these two, what do you see? What is that? What kind of term? Linear? And that's also a linear? Right? But the power, if I multiply this together, that's x squared, right? What's the power on the top? X cubed. So since I have a bigger power on the top than I do on the bottom, I've got to divide. So I'm going to have to come over here to the side and say, all right, I need to divide the bottom into the top. Now the only way I know how to do that is to actually multiply that back together so that I can divide, which would give me x squared plus 2x. So I'm going to take this x squared plus the 2x, and we know with division we like to fill in spaces that are missing with zeros. So take that x squared plus 2x, and I'm going to divide that into the numerator, which is 4x cubed plus 9x squared minus 2x plus 6. And remember, if you're missing any spaces, plug a 0 in there to hold that space. Right? Remember long division? Hopefully you do. So, what's my first step? X squared times what gives me 4x cubed? 4x. So I'm going to write that 4x up here, and then I'm going to multiply 4x by all of that, which gives me 4x cubed plus 8x squared plus nothing. And then what do I got to remember to do? Change my signs. And when I combine those, I get a positive x squared minus a 2x, and then I drop down to 6. Now, I can still do one more step, right? Because powers are still, they're not smaller here. I go until it's smaller here. So x squared times what gives me x squared? 1. Put a 1 up there. 1 times this. And then one more time. Change my signs. And what do I end up with? Negative 4x plus 6. Now, be careful. Remember my goal. My goal is to do a partial fraction decomposition. What do I have here? This has been divided, and I now have left 4x plus 1 plus what? That over this. So plus that over that. Now again, I wish you knew integration. If you knew integration, like when Helmers is reviewing this with his BC kids this year, they'll be like, oh yeah, I already know how to integrate. And when they look at this, they're like, oh yeah, I can integrate that easily. Oh yeah, I can integrate that easily. Ooh, that I cannot. So what do I do now that I have a fraction whose denominator is smaller than the numerator, but I can't integrate it? I do a partial fraction decomposition. Now, it's really easy on these to forget to do long division. If you forget to do long division, what you're going to end up with is, believe it or not, the correct partial fraction decomposition, but you're not going to have this part. And that part's part of it, right? You're doing a partial fraction decomposition, but technically those are fractions, 4x over 1, 1 over 1. You have to have this part. So if you don't do the division, you're going to get a little bit of credit for that problem, but not much, because I'm testing your knowledge of, do you know to do long division first? But now I'm going to go and say, all right, now that I've got it at least to this, all right, that's a great start. Now I have to work on this part, okay? So this is where I go, all right, I'm going to take that part, negative 4, and I'm going to leave this part alone for now. And I'm going to take that part, put it over the x and the x plus 2, and start the rest of my partial fraction decomposition. So what would you put this? How would you begin the process of rewriting this? What would my two fractions be? X in the denominator and x plus 2 in the denominator. And how would you describe those denominators? Linear. So what goes in the numerators? Constants. So A and B, C and D, whatever you like. And then what's your first step? So the common denominator is x and x plus 2. Now, we've done this enough times that I think you can probably handle this in your head. What happens if I multiply the left side by x and x plus 2? What am I left with? Negative 4x plus 6. What happens if I multiply the right side by x and x plus 2, each term? What do I end up with on this term? The a and the x plus 2. And the b and the x. Are y'all able to see that without rewriting it? If you're not, don't do it. I mean, go ahead and just write out x plus 2, x plus 2, x plus 2. Cancel what cancels, and you'll get down to here. Now, on this one, can you see some cleverly, carefully chosen x values that would work nicely for you? Talk to me. Negative 2. So I'm going to let x equal negative 2. And it's good to state this so that the person reading your paper will know what you're doing. So a negative 2 there gives me 8 plus 6 is 14. A negative 2 there makes the entire a value go away. And a negative 2 there gives me negative 2b. So b is -7. What would another one be? 0, which even if it wasn't 0, I'd probably pick 0. I mean, even if it wasn't, I was not able to see it, I would always pick probably 0 or 1 or something else. But here, 0 works great. That gives me a 6 on the left, and a 2a, and an a is 3. And at this point, am I finished? Would I be finished if I said this? 3 over x plus -7 over x plus 2. Is that my partial fraction decomposition? No, because what did I still forget? The 4x plus 1. So my complete partial fraction decomposition would be this. And if I were to give this problem to my calculus class and say integrate it, it would be child's play for them. If I were to give them this and integrate it, they go, we can't do that. Which is how it should be in AB, because you haven't learned this. And even if you had learned this, if you're in my, assuming I'm here and you're here, if you were doing an integral like this, there's a good chance you would have forgotten all about this since it is January. And next year we would be doing this kind of stuff in December, so it's been a long time you'd be removed from it. You tracking with me? Okay, I'm going to give you a couple really ugly ones in the last 2 or 3 minutes. We are not going to do the complete partial fraction decomposition, but I do want to see if you are able to start the process. So I'm going to give you some really ugly looking ones and see if you would be able to actually get somewhere with them. And if you can do this, you're going to be in great shape on this section. And you probably won't see this again until we get the test. So what if I gave you, I'll just make some junk up. What if I gave you this? Tell you what. So how would you begin the partial fraction decomposition process? What do you have there? Now this is tricky, right? Actually a lot trickier than you think. What is that? Is it a cubic? It could be. And if it was a cubic, wouldn't you write this? Hey, that's a cubic. So what would go on the top? Quadratic, which would be ax squared plus bx plus c. Right? But wait a minute. What's ax squared over x cubed? Think with me. What's that over that? What's that over that? A over x? What's that over that? B over x squared? What's that over that? Doesn't this look right here like I have thought about this as a linear term cubed, an x value cubed? And if it was a linear term cubed, shouldn't I have linear to the first, linear to the second, linear to the third? Constant, constant, constant. This is how I want to write that. I do not want to write it like this. Are you seeing this? So I know it's tempting to say, oh, it's a cubic, put a quadratic. But there's a better way to do this, and it's that. Okay, jump to the next term. What do I do with this? What is that? A linear squared. So it's a linear term squared, so how do I write it? Linear. And then what? Linear squared. And since it's linear, what goes on top? Another constant, so d, e. And then finally, what do I have here? Quadratic. And what do I do with the quadratic? Linear on the top, so what goes on the top? Are you seeing this? All right, guys. Enjoy your day. Good times.